Hey, calculus fans. Here's a chance for us to apply some of the stuff that we've been learning over the last few weeks. Applied absolute maximum minimum exercises. And we got some good ones, some very nice ones. And I say that with a smile on my face, but in utmost sincerity. We will enjoy doing these and feel a sense of accomplishment when we're able to do them. Here's a typical applied maximum minimum problem. Farmer Joe has 300 feet of chicken wire. Chicken wire fire? No, I don't think so. You know something? I'm going to have to fire my proofreader. Okay. Farmer Joe has 300 feet of chicken wire fence. He intends to use all of the fence to construct a rectangular pen. A barn will serve as one side of the pen, so no fencing will be used on that side. However, he will use some of the fencing to partition the pen into two smaller pens of similar shape and equal area. What should the dimensions of the pen be so that the enclosed area is as large as possible? Nice exercise. So here's step one. Determine what it is that we want to maximize or minimize. Give it a name, in other words, call it some variable maybe. Now, the name that we give it will probably depend on what it is that we want to maximize or minimize. And the question reads, what should the dimensions of the pen be so that the enclosed area is as large as possible? So what do you think it is that we want to maximize or minimize? We want the enclosed area to be as large as possible. So, aren't we trying to maximize the area? And we'll give it a name. We'll call it A. We can call it anything that we want, but if we're smart, we'll give it a name that will immediately remind us of what this variable stands for. We see A, we're going to think area. So this is a good name. Now there is another part to step one. Draw a picture or pictures where appropriate and this might be an appropriate situation to draw a picture. It's a physical situation and no picture has been given with the stated problem. So at least one picture would be most appropriate, and maybe more than one picture. We'll see. So I remember that a barn forms one side. So I'll write myself a little note here that on this side there is no fence. The pen is rectangular, so here's my pen. And even though there's no fence on this side, we were told that the farmer will use some of the fence to partition this pen into two smaller pens of equal size and shape. So in other words, we're going to take some of that fence and draw it right down the middle here, dividing this pen into two smaller pens. So apparently the length of this distance and the length of that distance are the same. I'll call them both x because I don't know what else to call them. So I guess the whole side has length 2x, right? And the length of this side, I'll call that y. So that'll make this side of length y also. Well, that looks pretty good. So let's see, we have, and let's see, this is a piece of fence. That will have length y as well. Okay. Well, I think we've done pretty good so far. Our second step, express the quantity to be maximized or minimized as a function of one variable. Now, what's the case? We're trying to maximize area, right? We're trying to maximize the area. And I should have written this out in step 1 before I got to step 2. But the area that we want to maximize is just the area of a rectangle, right? We know how to do that. The area of a rectangle is the length times the width. So that's what we're trying to maximize. And here's length, and here's width. Now the problem is the function that we want to maximize is a function of two variables, x and y. And in our max-min exercises, we never maximized or minimized a function of two variables. We only have experience maximizing or minimizing functions of one variable. So this is why step 2 is important. This quantity that we have to maximize or minimize, we have to express it as a function of one variable. And there's a key here. Usually in this second step, we use the same trick from exercise to exercise. So typically we refer to a restriction stated in the exercise to do this. To be able to express a as a function of one variable, we need to refer to a restriction stated in the exercise. Now, what do you think the restriction is? We can make this pen as long as we want and as wide as we want, as long as we use exactly 300 feet of fence. That was the restriction. And we're going to use exactly 300 feet of fence. We're not going to use any less than 300 feet of fence because we're trying to make the enclosed area as large as possible. And we're not going to use more than 300 feet of fence because we don't have any more fence. We have 300 feet of fence. We're going to use every bit of it to make this pen as large as possible. So that's the restriction. Now I guess we just have to figure out how to use that to write the area as a function of one variable. 300 feet of fence, which means that these three pieces of fence of length y plus these two pieces of fence of length x have to add up to 300 feet. So 3y plus 2x equals 300 feet. And now I guess the thing to do is to solve for x in terms of y, or solve for y in terms of x. So I'll move the x to the other side, and I have 3y equals 300 feet minus 2x. And that tells me, when I divide both sides by 3, I get y equals 100 feet minus 2/3 x. And here's what I'm going to do. I'm going to take this expression for y and plug it into the equation a equals 2xy. So I'll stand away from the screen and let you look at that for a minute. So we have the expression a equals 2xy. And I'm going to take this expression for y and plug it into this equation for y. Y equals 100 feet minus 2/3 x. And then I'll distribute the 2x to each term. So I'll get 200 feet x minus 2x times 2/3 x is 4/3 x squared. So I have a evaluated at x equal to 200 feet x minus 4/3 x squared. That's the function that I want to maximize.